Okay, so this is the design project for MEMS 0031, Introduction to Circuits by me, Ian Shirk. So, the task of my circuit is very simple. I'm making a double-sided light switch with a backup battery in case of power outages, which is represented in this circuit, the light by an LED, the battery by a capacitor. So, for the circuit analysis, so this is the sketch. As you can see, there is a switch leading into node A. Well, there's node A, which is the center for all my calculations from here. There is a switch connecting the voltage to the main right loop, and then two single pole double throw switches on the right, where if either one of those is flipped, current is cut off from the LED, thus turning it off. So, and then you have, of course, the capacitor in the middle, which acts as the backup battery. So, circuit analysis was done through the KCL equation at node A. So node A would be up here, as you can see. So we have three currents that are moving through this: I1, I2, and I3. So I1 is moving into node A, I2 and I3 are moving out. So as you can see from here, we have Vn minus Va over 47 ohms based on this resistor is equal to Va over 47 ohms, that's this one, plus 0.1 farads multiplied by dVA over dt. That represents the current moving through here. So after this equation was set up, it was then solved as a first order differential equation, allowing me to solve for the voltage across the capacitor, eventually giving me a VA, voltage across node A value of 0.5 Vn, Vn in this case being the voltage of the battery, minus 0.5 Vn multiplied by the exponential to the power of negative 2 over 4.7 t. So, a system of equations was developed for MATLAB. MATLAB is used in symbolics based on the original KCL equation, allowing for quick solving of all properties at any value of t or Vn. So for my purposes, I used t equals 1, Vn equals 3, as I used two AA batteries, and the ideal voltage of those two AA batteries are 3 volts. So to check that the values generated from my analysis were correct, the conservation of energy of the circuit was checked, also using MATLAB, confirming that energy supplied is equal to energy dissipated. So work is here. Over here is the values generated from MATLAB for t equals 1 and Vn equals 3 volts. So, you have all of the voltages and all of the currents, and then you have P1, P2, P3, and P4. Now, P1 is the power supplied by the batteries. So that is P supplied. P dissipated is P2, P3, and P4. Now, if you add these together, which if I do that now, so you have 158.3, oh, sorry, apologies for the handwriting, is equal to, then using my calculator, 130.9 plus 5.8 plus 21.7. That gives you 158.4. Which, while there is some deviance there, that is most likely due to the computer's rounding, it checks out. So the values generated by my analysis are correct. So, the prototype. How this all works is that in order to get the 3 volts, or above 1.5 volts needed for the LED to actually light to a visible level, I have two AA batteries wired in sequence. That comes through, hold on, let me change to a better color. That comes through the positive out through the resistor into the switch. That comes into two loops. One through the capacitor back into the negative. The other through the switches, where if either of these are flipped, current shuts off. But if both but if current is going through, it goes through the 47 ohm resistor to the LED to the negative. I will now display that the prototype through a video.
So this is the circuit that I designed, or at least the model of it with the breadboard. So in order to get the 3 volts I needed to get the LED lit to a proper level that's visible, I chained 2 batteries in series to get to around 3 volts. And then here is the main power switch. If this is flipped, then the voltage from the batteries is running through it. So I'll go ahead and flip that. Now when that's flipped, it comes in, it goes through the resistor so that the capacitor and the LED get voltage, right? Now there's 2 loops that 2 paths it can go through. One through the capacitor, which charges through this. This is the backup battery. The other through the double switch. Now this is a 2-way switch, so if either of these is flipped, the light turns on. So you can turn it on or off from either switch here. So like, let's say this is in a house, you could have one switch at one side, one switch at the other side of the room. Both command the same light. Now the capacitor is the backup battery. Let's say it's like a storm battery in a house. So if the power were to go out, it would still have some light. So this is displayed. I'm sure the capacitor is charged up enough. But if I turn off the main power, even though it dims a little bit, the light stays on for a good minute or so after I turn it off. Now obviously this would be a much larger scale in an actual house, but this is my circuit. And after the main power is turned off, of course the switch still works. But yeah, that's pretty much what my circuit does, and it's well prototyped. It does all the behavior I intended to do.